Okay, hello everyone. Thank you very much for joining us here for the Built for the Cold Engineering in Winter Sports seminar run by the Institution of Mechanical Engineers. I hope you can all see the screen. Please let me know if you can't, but my name's Tim Carew. I'm the chair of the session today. I'm also the incoming chair of the Sports Engineering Group at the Institution of Mechanical Engineers. I'm delighted to say we've got two excellent speakers here for you. I hope you're all enjoying the Festival of Winter Sports that's currently going on across northern Italy. Some really exciting and interesting activity there. Lots of interesting, let's say, sort of conflicts between competition, engineering, human endeavour, lots of controversy as well, perhaps for us to unpack afterwards. But I can say today we've got two fantastic speakers. We've got Dr. Fabio Malizia from Heriot-Watt University. Fabio will be talking to us about aerodynamics in winter sports, of which there has been some discussion in recent weeks. And we also have Dr. Will Dauber from Imperial College London, who will be speaking to us about helmet impact testing in snow sports. And again, certainly from the Team GB perspective, there's been a combination of those two things that's been discussed recently. So something for us to unpack. I'd just like to start by introducing the institution to those who may not be aware. So I'm pleased to say we had over 100 people registered for the webinar, so we've got a really varied audience coming to us from all sorts of places. So I wanted to just quickly to introduce the Institution of Mechanical Engineers. So who are we? So we're a community of engineers, and the core mission of the institution is to improve the world through engineering and to try and do that in a way that's aligned with sustainability, inclusivity targets as well, and making the world a better place for everybody. In terms of sports engineering, the institution has quite a long history of engaging with sports competitions. So we have a very long-running engineering competition, actually the most established engineering competition, educational competition in Europe, which is Formula Student UK, has been running since 1998, very strongly supported by industry and academia. That's been running for, as I say, for over 25 years. In recent years, Formula Student has expanded to take into account developments in computer science, artificial intelligence, and hardware. So we have a Formula Student Artificial Intelligence Autonomous competition, which is very well supported and growing year on year. As a group within the institution, we're relatively new. So the group is part of the biomedical engineering division within the institution. Whilst as engineers, we recognise that our day-to-day activities are sort of grounded in technological developments and technology. We recognise and we need to appreciate that all of our work is actually human-centred and athlete-focused in the sports engineering world. So we need to keep them at the core of what we do. So as I said, yeah, part of the biomedical engineering division, so we have lots of crossover with those human factors. We're an active community of sports engineers that is open. We're open to academia and we're open to industry. So if there are people on the call who are perhaps coming from those environments who'd be interested to join us, to join the conversation and to become involved with the sports engineering activity that we're trying to pull together within the UK, please contact the institution afterwards. I'll put some contact details up on the website, sorry, on the slide afterwards. We do have a website, so if you put into the search engine of your choice, IMechE Sports Engineering Group, you should find our landing page. We are, as it says, sort of on the top of the screen there, a community for sports engineers, and that's really what the ethos of the group is all about. In recent years, we've been developing policy and advising industrial partners too. This started around the London Summer Olympic Games in 2012, with the institution put out the report Sports Engineering: An Unfair Advantage, taking into account sort of sports engineering activity in the UK and how that can benefit both the wider economy and the society as well. Um, about 10 years sort of after that report was published, we've revisited some of these aims and to see whether those things were happening. So we have the Sustainable Inclusive Innovator Report, which was launched in October 2023. And last year, or sorry, in 2024, we had Engineering Better Sports Venues Designing for Athletes, Spectators and the Environment. So again, thinking about that crossover between human factors, human-centered design, the built environment, inclusivity, sustainability too. Last word is that we're also supporters of the annual International Sports Engineering Association Sports Engineering Seminar Day. I have a picture on the slide there from actually one of the first, which was probably around 2017. So these have been going for about 10 years. I'll have a little bit more on that at the end of the presentation today, or the webinar today, as Fabio is co-host for this year's edition, and he'll have a bit more information on that for you guys if you're interested. So I think without further ado, I will stop sharing and hand over to Fabio. What I'd like to say before we get started is that participants can interact with us during the presentations, during the webinar as well. So please use Zoom's Q&A function. So you should all see that in your control bars on the screen. So if you just open that, please feel free to drop in questions whenever you want during the webinar. Those will go through to our IMechE webinar team, very capably led by Becca today. Becca will be sorting out the questions behind the scenes for us as we speak. So we'll have a set of questions for Fabio, set of questions for Will, and after both speakers have presented, we'll have about half an hour of speaking across the two talks. We'll have about 20 minutes at the end of the webinar just to address the questions that are in the chat. And I've got a few as well in case we don't get too many, but let's see how we get on. So without further ado, Fabio, I'd like to just say over to you. If you could please start sharing your slides, then Will and I will drop off and you can get started.
Thank you very much, Tim. Can you confirm you can see the slides?
Yes, I can see that perfectly.
Perfect. Thank you very much. So in today's webinar, I'm going to talk about aerodynamics in winter sports. Before diving into the results, I would like to introduce two main concepts. So the first one is that small improvements, really details, can make a difference between winning or not. If you don't believe me, check these races. In a Garmisch downhill alpine skiing 2025, Federica Brignone won against Sofia Goggia by only 100th of a second, 1 cent. And if this looks impressive, in the World Cup 2023-24 of huge races, Rings won by only 1,000th of a second. So you can really imagine that really small details can make a difference between first, second, third, or fourth places. And these are not the only examples. It's really, there are many, many, many like this, just by a few cents of a second. So as a sports engineer, we often hope to improve the performance of the athlete by really a lot, but often we really look by these small, tiny bits that they can really make a difference, like marginal gains that can turn like from a second to a first place or that. So this is the first key point that I want to stress. The second is that for people that are not aware about aerodynamics, is that aerodynamic forces are proportional to the square of the velocity, which means that if we go faster, the aerodynamic forces will increase. So this is just a summary of different sports. And if we focus on winter sports, we see that many of them are on the right side. So a lot of winter sports, you travel at a very high speed, like in luge, ski jump, skiing. It means that so the athlete is really subjected to a large forces. The main one is the drag force, so the resistive force, the one is trying to slow you down. But in competition like ski jump, you even have lift, so the force that is pulling you up, that helps you also to fly for longer speed. Other competition, for example, I want to stress this cross-country skiing because I'm going to talk about it later, is that what I'm showing here is not really the average speed. The average speed is more on the left-hand side, but in this type of races, you have a lot of segments and you have also downhill sections where you reach these 60 kilometers per hour, but the average is lower. But still, aerodynamics plays an important role over there. So aerodynamics, you can start to understand that has quite a big role. But if we think to aerodynamics, we always think that it's something very recent, maybe last 10, 20 years, people are interested in aerodynamics. So but if so important, probably this thing is not really, people should have analyzed even earlier. And actually they did. So while I was searching for first aerodynamic test, on LinkedIn, I found Andres Hauser from RUAG that posted this, that they, in their company, they did alpine skiing wind tunnel test already in the 70s. So we are talking about 56 years ago. And here you see all this pulley system that connect the skiing to the overhead balance. Then I was curious, I started to have a look also to possible other wind tunnel tests. This one, probably the one in the picture, is one of the first. There were other innovations where there were some claims about aerodynamic advantages. For example, one-piece racing skiing suit. Moncler introduced the first Leica skiing suit in 1968, and there are aerodynamic improvements on the fabrics and the skin suits. So probably the first wind tunnel tests in ski or alpine skiing were at the end of the 60s, beginning of the 70s. After finding this, I was quite happy until yesterday, when I found that Virma Virta in 2016 talked about wind tunnel tests performed by Stroman in 1926. So we are really talking about 100 years ago, which is quite impressive. So people knew about the role of aerodynamics. Other wind tunnel tests of ski jumping were performed in 1955 with Andreas Drescher, which was a famous ski jumper at the time, where he really improved his position by leaning more forward compared to other his competitors. So it was really used also not only to know something about the sport, but really to optimize the position. So this was the past. What are we doing now? Now, you already see this wind tunnel test in the Silverstone Sports Engineering Hub. You don't see anymore the pulleys. We have force balance embedded with the tunnel, the luge connected to it. So we have better ways to test, but also not only wind tunnel tests. Nowadays, we are performing also a lot of computational fluid dynamics. I will talk about it as CFD. This is a simulation of an alpine skier. But that's not all. Aerodynamic data are also combined with GPS motion tracking, video kinematic models. And I'm not talking here, but there is also another field test activity, which is called the Ring of Fire, where they were testing, for example, ice skaters on a track, and they were gaining aerodynamic data from these real athletes moving around the track. And after all this introduction, what I'm going to talk now is about results that were published in the Sports Engineering Journal, because I'm part of the editorial board of the journal, and I was also guest editor for a topical collection in fluid dynamics in sports. So first one is Elfmark et al., talking about aerodynamics in cross-country skiing, and then two papers from Giliarus et al., which talks about alpine skiers' aerodynamics, about the position of the arms, how they influence. And also a CFD methodology that is used to move the athletes in the virtual environment. And two of these papers were part indeed of this topical collection, co-authored by me, Dr. Zignoli, and Professor Giliarus. So cross-country skiing aerodynamics. So cross-country, there are long races, and you have different segments where you can go uphill, flat terrain, or downhill. And so there are different sub-techniques where the athlete, the skier, is gonna ski in a different ways. So think to a car where we have gears. Here, the name is really used in the same way. So you have a low gear, so gear 2, for example, when you are going uphill, where in this case, you have one pulling, so one push every second leg stroke. When you're going moderate uphill on a flat terrain, then you increase the gear, you go gear 3. And here you have one pulling each leg stroke. Then gear 4, you can think it is now flat terrain or slightly downhill. You have one pulling every second leg stroke. Gear 5, you don't pull anymore, you just skate with your skis. They also introduce another position, which is more a tucked aerodynamic position for really steeper downhill. So they investigated the aerodynamics, but the first activity they've done is to do frontal area measurements. So they used a green screen and a camera, so they could take a picture, remove the foreground from the background, and then with a reference dimension, they could convert the number of pixels inside the weight area to the frontal area in terms of meters squared or centimeters squared. This was done for a reason, because in the drag formula, there is this term, which is frontal area. So the drag is half density, drag coefficient, frontal area, square of the velocity. Remember, I mentioned at the beginning, the square of the velocity. So they did this for two athletes, and they compared their frontal area, is what you see in green. So the second athlete was consistently having a larger frontal area than the first athlete. However, different position had a different frontal area difference. So gear 3 had 5%, gear 4 around 7%, gear 5 2. So it really changed the frontal area difference between two athletes, depending on the position they're using. In the picture here above, you have the different phases of a gear 3 phase. Then they performed the wind tunnel test. They reported the results in terms of CDA, so the product of the drag coefficient and the area. And similar to before, also the second athlete had also a larger drag area than the first one. But Also, it was different. It was around 7% and a bit more than 8 in the two different positions reported. And also, the drag area increase was larger than the frontal area. This is a very interesting result because it means that the frontal area can give you a trend, but if you really want to know the drag of the athlete, you really need to perform a wind tunnel test or safety simulation. So you cannot only base your results on the frontal area, which still is quite a good indicator. So then they reported the results of aerodynamic drag, including also information from GPS data. So this graph looks complex. I'm going to explain in a second how it works. So you have two vertical axes. The one on the left tell you the fraction of time a certain position at a certain speed is used. So let's have a look of these vertical bars. So the blue one is gear 2. So at 3 meters per second, gear 2 is used for 2.5% of a race. They did this for, I think, one or a few races. So instead, at 4 meters per second, you have the sum of the gear 2 and gear 3 is used around 3.5%. So you need to read the graph in this way. On the right, you have the information about the wind tunnel test. So the drag area, CD, drag coefficients, time frontal area. The first result is that the drag area decreased significantly with the speed until 10, 12 meters per second, while especially for the most aerodynamic position, this tucked position in green, the aerodynamics drag area doesn't really change with the speed, so it's kind of constant. Second result is that the three positions which have similar frontal area, G2, G3, and G4, actually the curves overlap. So it doesn't really matter which is the position you are using. The aerodynamic drag, it's pretty much the same at a given speed. Of course, you see this decrease with the speed. However, when we go to positions that are more aerodynamic, so G5, where you're not pulling anymore, you're just skating, or G6, where you're not even skating, you're just tucked position, you can achieve quite a big aerodynamic improvement, for example, by tucking your arms in front of you, 22% reduction in drag. And with the tucked position, if you bend your knees instead of having straight legs, the aerodynamic drags reduce by 23%. So quite interesting results. You see this position, even if it was for a little part of the track, even the green one, it's still used in a race. So it's important to optimize the aerodynamics also of these segments. So this is about the cross-country skiing. Now I'm talking about the paper of Giliarus about the aerodynamic influence of an alpine skier arm. So they performed both wind tunnel tests, again with two participants, and CFD simulation, but only on one participant, number B. They also consider three positions: the low tuck, which is the most aerodynamic with these bent knees; the high tuck, which is used, for example, when you turn or you are in an even surface. It's less aerodynamic, you can imagine. And then the flat position, because there are some parts where you're even flying in these races. I'm going to talk about only the low tuck and the flat position. So the focus was mainly on the arm positioning. So what did they find? Is that the forearm, when is parallel to the ground, we say that is 0 degree. When you move upwards the forearm, the degrees, it's positive angle. So on the x-axis, we have the arm angle. On the y-axis, we have the relative CDA. So the CDA divided, so the drag area divided by a reference drag area. Now, what we see with the markers, which indicate the wind tunnels, but also the marker with the line, which is the simulation, that the aerodynamic drag area decrease. It reach a minimum around 25, 30 degrees, and then it has a steep increase. So this is a good information for a skier because he knows that if he will pull up his forearms a little bit, 20, 25 degrees, his aerodynamic drag is going to decrease. From CFD simulation, they also gained some more flow visualization that can explain the behavior. Is that when at a 0 degree angle of the forearm, the flow goes smooth on the forearm, but then it hits the upper arm and the leg at higher speed with some more recirculation. While when the forearm is inclined of 22 degrees, you have a slightly higher drag on the forearm, but then the flow goes smoother around the upper arm and the leg. So this explains why this aerodynamic behavior. This decrease at 25, 30 degrees. Then they investigated the flight position compared to the baseline low tack. So when the skier has the arms down, the drag area increases really significantly. It's even better to have arms on the side, which, for example, it's helpful to have some more balance. But the best position is to have the arms along the torso backwards. And the second good best one is to have the arms behind the legs. And actually, this position is used by several skiers. I've seen some pictures. However, when we do this in CFD simulations, every time we need to do a 3D scan. So probably it would be nice to have a system to optimize the position of an athlete without redoing a 3D scan all the time. So what they develop is this virtual skeleton methodology. So they perform one scan, and then they move the joints to also to have the capability to achieve every type of position. For example, they perform 2 scans of an athlete at a low tack and the athlete standing. Then they modify with the virtual skeleton methodology the position to assume the low tack position, and the drag difference was 2%. So it was really a successful method. Now, I've talked about a lot about aerodynamics. If you want to know more, there is this paper that I suggest, is Brownlee 2021, Aerodynamic Drag Reduction in Winter Sports, the Test for Speed. This focuses mainly on wind tunnel tests and skin suits. Not a lot about safety, but it's really an interesting reading. So to conclude, we have seen that races can be decided by small time differences. Aerodynamics have a large impact on athlete performance. Aerodynamics is athlete dependent. We will see that the different drag area for different athletes. In cross-country skiing, we saw that the change in drag area are not only determined by the frontal area, drag area changes with velocity, and the more tacked position reduces drag area. For alpine skiing, the arms has a lot of influence, and the virtual skeleton methodologies reduce the need for 3D scan. So thank you very much, and open for question later.
Excellent. Thank you, Fabio, so much for that. I can see that we have some rounds of applause coming in, so well done. It seems like that was enjoyable, and I can see we've got some questions in the Q&A as well, so we'll definitely come back to those later at the end of the presentations.
Thank you.
Thank you again. Will, I think we're ready for you. If you wouldn't mind starting your video and sharing your screen, then we can get straight into your talk, and we will come back, as I say, to the questions after that.
Absolutely. Thank you very much. Right.
We can see. I can see your PowerPoint. There you go. Perfect. Yeah, that's gone into presentation mode. Off you go. Thank you.
Thank you. Right. Well, really great talk from Fabio there, and it was good that he was showing how sports engineering can be used to kind of extract every bit of performance. But another big aspect of sport engineering is also keeping our athletes and anybody who loves sport safe and doing what they do in that sport. So I'm going to be talking a little bit about how helmet impact testing is used for ski and snowboarding, current practices, and what we can expect the future of these tests to look like as well. So just a little demonstration to start on how these kind of injuries can happen within ski and snow, despite whether you're an elite athlete or recreational. You can see from this the importance and why we need to make sure these helmets are up to scratch. And there are some quite staggering statistics in terms of how head injuries lead to major trauma in these sports. They account for around 50% of major trauma, and they are actually the leading cause of fatality within skiing and snowboarding as well. To make sure helmets are of quality, there is a minimum requirement for them to be distributed across the world, but I'm going to be speaking mostly about BSEN 1077, which is the British and European standard for skiing and snowboarding helmets. The procedure is relatively straightforward, quite common from what you'd see in a normal helmet impact testing procedure. It's a guided drop of an adult-sized head form, which is fitted with a triaxial linear accelerometer. And that head form, when fitted with the helmet, is then dropped at a speed of 5.42 meters per second onto a rigid steel anvil with a face that's perpendicular to the impact vector that you can see. And for that helmet to then be sold, what has to happen is that the peak linear acceleration reading has to be lower than 250 G, or else it isn't going to be valid. There are US equivalents to these standards as well as the rest of the world. And there are also some requirements in competitive sports, high-speed sports, such as Super G and things like that, where the helmets follow the same procedure, but they are tested at a slightly higher impact velocity. So why do we measure PLA, first of all, in these standards? Now, PLA is a good predictor of focal injury. And what I mean by focal is it's injury that's concentrated around a very specific area of the brain, quite a small area. And these typically correlate well with skull fracture risks and potentially things like extradural hematomas. And they usually occur at the coup part of the brain, which is near to where the impact point happens, or the contra-coup, which is the opposite side of the brain to where these impacts happen. And if we switch this back into helmet design, looking at this line graph, we can see what a helmet does to actually reduce peak linear acceleration. So the red curve shows a less protective helmet design where PLA is high and that impact duration is low. Whereas the blue curve, what that's doing is it's extending that impact duration to attenuate some of that energy and bring that peak linear acceleration much lower. So that's typically what you'd expect from a better helmet design. However, what the standard doesn't consider is a whole other mechanism of brain injury that happens alongside those induced by linear acceleration. And this is due to the rotational motion of the head. What happens in these scenarios is the brain inside your cranium is suspended within something called cerebrospinal fluid. And what happens is if your brain experiences a sudden acceleration, your head, then the brain lags behind. And what that causes is quite immense shear tissue strains within the brain, and they can lead to life-altering, potentially even fatal injuries. And it's something that the standard doesn't consider at all at the moment. A little mechanism I'm showing on the right-hand side here is diffuse axonal injury. That's an example of a particularly bad rotational induced injury that's at best really going to change who you are as a person, at worst often leading to fatal. And we have a lot of different metrics that we use to predict these rotational based injuries, but I'm giving an example here of the brain injury criterion BRIC, which is based on the rotational velocity of the head, which is designed specifically to predict the onset of diffuse axonal injury. But there are many that we can choose from. So does this mean helmets aren't safe? No, it doesn't. The standard is providing a minimum requirement, and what we can see from the data is that current helmets are reducing certain injury risks, and they're also reducing things like ambulance and helicopter journeys onto ski slopes, so less demand on the actual society as well. But there are some concerns that we can see. So looking at the data, there seems like there's a less significant reduction in intracranial injuries, and most of these are formed by rotational head motion, so that makes sense. And also there are some concerns suggesting that when we then test these helmets on a more compliant surface, such as snow, which as you can expect is in abundance in these sports, then actually the helmets are performing less good than what they do in the lab conditions. So my question then is, do we need to wait for these standards to change? Or is there something that we can be doing within research? Standards take a lot of time to change. And the reason for that is they're built from a committee of experts who are usually volunteers. So as you can imagine, that takes quite a bit of time, but then they often have very conflicting interests. And another thing is they need to make sure that this standard is right. It's the best interest for the sport. It's the best interest for the people doing it. And so rightfully so, they should take time. Research, on the other hand, can be a lot more agile. We can be much more adaptive to knowledge that's coming through, such as new knowledge on head injury risks, new knowledge on how the injuries are happening, head impact mechanics. And so we can really adapt and really push designs by having our own research-based method that is separate from the standard. What it then also does is, rather than just being a minimum requirement, it's then also a way of differentiating the quality of that design beyond just that it is meeting a certain standard. I'm showing a picture of a car here, which you might think is quite weird, but I think it's a really good example of why these research-led safety ratings can work. This is the Euro NCAP, the new car assessment program, which has run for nearly 30 years now. But what they did was they looked at how road traffic accidents were happening, started testing cars. All of a sudden, big manufacturers were flooding in, trying to get their cars rated so that they could advertise 5-star safety ratings with their products that they were selling. And it was estimated that in the first 20 years, nearly 80,000 lives were saved in road traffic accidents just due to Euro NCAP alone. So what we wanted to do was say, well, could we recreate Euro NCAP effectively for helmets? And we started by looking at cycling as an application. And one of the things we did was we took real world data where road traffic accidents were happening. We were able to recreate those in simulation using multi-body dynamics to then work out what those head impact factors were. And alongside reviewing the literature, we were able to build this really clear injury of what caused severe injury in cyclists. And from that data, we were able to then recreate a lab test that's similar to the standard, but induces rotational motion. And what that allowed us to do was actually really rate the performance of current helmets that were being sold on the market. And from the videos here, you can see an example of a helmet that's really good at attenuating rotation. You can see the neck doesn't really change much from being horizontal in this impact, compared to a helmet where it seems rotation isn't really a factor in their design. And you can see that neck's rotating a lot more. So there's a big difference in the injury risk between these helmets. In terms of the implications of this, what we wanted to do was provide this information to consumers first and foremost. So we had a consumer-facing website. In little over a year, we had over 130,000 views. One of the biggest retailers of helmets in the UK actually dropped the price of some of their best performing helmets because they wanted to make them more accessible for people. And we've had a flood of lots of different manufacturers coming in now trying to work out how they can improve their helmet designs and then can they potentially launch with the safety ratings. Exactly the same thing as what happened with Euro NCAP. The figure on the top right shows the disparity in linear risk on the left-hand side between the first 30 helmets we tested and then rotational risk between the first 30 helmets tested. You can see how much more spread that rotational risk is. And that's because not all helmet manufacturers have to consider it in their designs. And potentially we can now push them to do that. Another thing I mentioned facing consumers. Another thing we found was that the price of helmets didn't have any correlation really with the risk that it provided, the reduction in risk that it provided, which when there's little information available to consumers, that's quite staggering. So hopefully our ratings can better improve that. So let's link this back to snow sports then. How can we translate this into a rating that is good, first and foremost, for skiing and snowboarding activity? So from reviewing the literature, we can see that people have already looked at kind of the causes of injuries. So the most common were caused by simple falls, but we can see that within the most common and the high risk of severe injury, there's causes by jumping impact and then impact with a stationary object are both prevalent in those. So they're quite a concerning mechanism that is worth looking at. In terms of the head impact locations, the rear of the head is the most common spot. That's quite rare, very different to cycling. And it's not actually a requirement in the current standard to impact the rear of the helmet. So that's quite interesting. Both linear and rotational induced injuries are there within the data, which is just validation for why we need to consider rotation. And then if we look at it, it's mostly males, more likely to be adults, and then a slightly higher injury risk among snowboarders than skiers. This paper is really interesting by Nico Bae et al. And what they were doing was using multi-body dynamics like we did previously to look at simple fall in snowboarding. And what they were looking at was what are the factors that influence, first and foremost, mostly head impact speed and then head linear and rotational acceleration. What they found for both was that travel speed and the person height were one of the main factors. And then for impact speed, body lean was important. And then for head acceleration, snow hardness was actually really important as well. And this is the data that we can really use to start forming this test method into, actually looking at the impact velocities we need, the head orientations, etc. Another thing they found that was quite staggering was that the head impact speeds in their data all exceeded the minimum requirements of the current European standard, but also the high speed condition used by the FIS for certain sports. So that is quite glaringly something that we need to address with our helmet impact test procedures. So what remains to know then? I've shown you what data is available there, what we can use to inform these test methods, but there's still more research that needs to be done so that we can make sure we're testing them to the best they can be. In the previous slide, they looked at simple falls, which are the most common cause of mechanism, but let's also look at what's causing severe injury. So collision with stationary objects, jump impacts, and as I mentioned previously, we also need to make sure we're understanding how helmets are performing on compliant surfaces and not just rigid surfaces. And then lastly, we need to look at how we're actually measuring and predicting this injury risk. And this it's quite a complex debate that goes on within the head impact world. These are the risk functions we use within cycling injury because we found they were best correlated with the risks that we were actually seeing on scans and actual injury data. And you can see they're based on PLA, linear acceleration, BRIC, which is based on rotational velocity. But we need to make sure the thresholds for these are valid for ski and snow sports first and foremost, and making sure that we're using the right metrics for those sports. Some key takeaways then. I don't want to put people off wearing helmets. They are good. They do reduce injury risk, but there is definitely room for improvement there. And we don't have to wait for the standard to address those. There is something that we can be doing to push that. It's quite a good space to be working in, really. Manufacturers seem very keen to push for this. They really genuinely want to help people. Unfortunately, what that means is we can really work to keep people within these sports, be them recreational, be them elite. We can keep them doing what we love and hopefully push these sports further and further without that concern of injury risk. Thank you very much to the IMechE for having me here, having me speak, and to Tim and the rest of the team. If anybody's really interested in this work, please do feel free to reach out to me. You've got my email, my LinkedIn. My current work is very much focused on child head injuries. There are currently no real developed risk functions models for predicting child head injuries. So I want to make sure that they're being represented in helmet testing procedures. And if you have any thoughts on any of this or just want to chat more, please feel free to reach out. Thank you.
Fantastic. Thank you, Will. Very, really entertaining, very interesting discussion. And yeah, I can see all the virtual hand claps coming through the screen as well. So lots of applause for you there as well. Well done. Fabio, if I could just ask you to pop your camera on as well, then I think we'll move straight into the Q&A. So just firstly, a couple of thank yous from me to both of our speakers. It's such an immense challenge to try and distill the general picture, but also enough technical detail to make it relevant from a sort of scientific standpoint into a 15-minute presentation. So we really set you a difficult challenge, and I think you both rose to it beautifully. So thank you for that. Fabio, I'll start with you. We have a question for you about arm angle, I think, during the ski.
Yes.
So the question was for the arm angle, were there any differences recorded between male and female athletes? And was there anything to account for perhaps biomechanical differences or the difference in body shape between the genders?
Yes. I'm gonna share the screen. I just want to emphasize that I'm talking about research from someone else, but in general, I didn't mention participant A was a female, participant B is a male. So you see that the trend are very similar, but for example, here there is a bit more scatter at arm angle negative. But in general, trends are similar. But when you want to optimize the aerodynamics of an athlete, it's very much dependent on the athlete itself. So if you really want, you can get trends that works for most everyone. But then if you really want to, if you have a top athlete, usually you really perform with an SFD simulation on that athlete because that is. And the biomechanics comment is very important. I mean, this is only aerodynamics, but the athlete doesn't work only with aerodynamics. He works with a lot of with biomechanics and many other aspects. So the focus is always to improve the performance. You can give the data about aerodynamics, but then you need to combine this with biomechanics and others to increase the performance of the athlete as much as possible. So it's always athlete focused, and you need to consider the entire picture.
Absolutely. Thank you. And I would just add to that, from my own research work in the world of competitive cycling, that this idea of having representative models in the simulation environment across different athletes, and particularly for para sports as well, it's something that's an area of ongoing research work. So, if people are interested in that, I think there's definitely scope for collaboration there and definitely more work to be done. But thank you for that. I think the next question I want for you, Fabio, was from James McDonald. So the question was about a range of positions, and I think this was for the cross-country skiing. So the question was, have these evolved naturally in skiers? So it didn't seem too much of a change in the first gears, if you like, I think you mentioned. And this was something I picked up on as well. It almost
Yeah.
seemed as if it didn't make a difference being in either any of those positions at the low speeds. But are there any suggested changes to best practice based on the test results?
Well, I don't know historically, but here again, it's a combination of biomechanics, aerodynamics, and others. Because in the low gears, you are really maybe focusing more on the pushing because you really need to go uphill, while in the others, you can also focus more on skating and also on the aerodynamics. So the aerodynamically speaking, the position didn't show much differences, and that is a bit. Oh, I don't have any more the sharing option. Okay,
Ah,
anyway.
don't worry.
No worry. I wanted to show the picture, and that's because the athletes were almost standing in both the gear two, gear three, in all the gear two, gear three, and gear four. In gear five, instead, it was bending more forward, so you could really play a bit more with aerodynamics optimization, like by tucking the hands in front.
Absolutely. Lovely. Okay, thank you very much for that.
Welcome.
I'm just trying to see if there are any further questions for the first talk. I don't think so. So I think we've covered those off. So thank you, Fabio. Will,
Welcome.
there are a few questions here for you as well. So if I just bring you into the conversation. Actually, I'll start with one from Tom Allen here, who's a member of our committee. So what are the barriers or challenges in transferring your work from cycling, for example, to snow sports? Yeah, do you need specific funding to do that?
Okay, yeah, that's a good question. I think one thing that is really happening within the head injury research is this move from the assumption that all head impacts happen in the same way, no matter what the application is. So looking at the cycling data, we really tried to push, let's actually see what happened in cycling. So we were looking at the road traffic accidents, the falls, the people who were getting involved, the injuries that were coming as a consequence of that. And we need that exact same data now for the snow sports stuff. So I showed what's there, and there's actually quite a good bit of literature there. There's enough to rationalize looking at it as an application. There's enough to start gauging, first and foremost, how maybe we should test the helmets. But what isn't there is this recreation now of these severe injury scenarios. And to actually achieve that, then yeah, we'd be looking at funding opportunities to fund year or two projects really would be probably enough to actually get this data, which would be fantastic. And it would require things like software licenses for multi-body dynamics analysis and things like that. To tie it in, one thing I should have maybe mentioned in the talk is that there's also a helmet rating scheme called Virginia Tech over in the US, and they do quite similar work to what we do, and it is really, really good work what they do. Now, they are based purely on assessing concussion risk. Now, concussion, we avoid it because it's a very vague term. There's no actual pathological signature of concussion. You couldn't ever look at a scan and diagnose it. It's based on headaches, dizziness, nausea. Often it's not even the result of a head impact. I think speaking on snow sports, skelly head, if people have heard of that in skeleton, is a really good example of how concussive symptoms can come without head injury. But yeah, what Virginia Tech do very well is they've rolled this out for many different sports applications, but they're using risk functions purely based on concussion risk in American football, which is quite generalized, very different impact mechanics on what happened in many other sports. So the funding, I think, needs to go towards this sport specific head impact assessment, and then we can make sure these ratings are really the best they can be for those sports.
Fantastic. Thank you. And you absolutely covered off another question that was here in the list about how the Virginia Tech ratings are different to the others that you've mentioned. So thank you for doing that already. I will just expand on that point because there's another question about MIPS, so the MIPS technology being sold in snow sports. So I wondered if you could just briefly introduce what that is for those who aren't aware. But the question from Duffin here is, have you seen any significant data showing that the MIPS is actually reducing risk in snow sports environments, particularly in reducing rotational accelerations compared to non-MIPS helmets?
Yeah, absolutely. So MIPS is the one that kind of most people go to. It's by far the most well-known technology for reducing rotation, but I'll start it off by saying it's not the only one. There are other ones out there. There's a relatively new one called RLS, which is a release layer system, which is looking quite promising. Coroid seems quite promising, and then there's others like WaveCell, etc. From the testing we've done, and actually we published this, was we were looking at cycle helmets with and without MIPS, so identical models. And in almost every case, we were seeing that the MIPS did reduce the rotational injury risk. It wasn't as if this helmet was completely unsafe without MIPS, it's completely safe with it. It just had a slight benefit, really, with all the tests that we did. Usually MIPS helmets are slightly more expensive, and it seems that if you can afford that slight price increase, then there is a potential that you would have slightly better injury risk reduction with MIPS included.
Lovely. And just building on that, could you briefly explain how the helmets actually prevent rotational also rotation, let's say, in the head and the acceleration in the brain then? Because that was another question we had in the chat.
Absolutely. Yeah. So I'll explain how MIPS works because I think it's one of the most simple ones to understand, really. So it's a slip layer that's within the helmet. If you look inside most MIPS helmets, you'll see like a very thin yellow bit of plastic, but there is actually a new model they've got called the Air Node, which is like padding. And what it does is it allows the helmet to first and foremost rotate across your head before your head then starts rotating. And that slight delay is enough to dissipate quite a significant portion of that rotational inertia. So it's not going to be the most protective feature in all impacts, but in an oblique impact, which are the most common, then it can provide a decent bit of protection.
Lovely. Fantastic. Thank you for that. I've got one more question for you, Will, and then I've got one more for you, Fabio, and I think we'll perhaps have to start thinking about wrapping up at that point. But so we actually spoke about this before your talk, Will, and there was the idea of developing a kind of converging on a single standard. And you sort of outlined lots of different ways of assessing brain injury, the biomechanics of it and the impact of it. Is there a single method that you think also researchers can agree on in assessing these things?
Yeah, it's a really, really interesting point, and it's massively debated really in our field. So I showed PLA and BRIC as the two kind of metrics that we've used. In actual fact, there's probably about 20 that are quite commonly used within research, and everyone's kind of arguing that theirs is better than the other, and they all predict slightly different forms of injury. Like I'm saying, we're talking about brain injury, but that is a massive umbrella term for the different kinds of head injuries that you can experience. One of our PhD students, Emily, is actually doing some really fantastic work at the minute about using machine learning models with actual in-sport data, so captured using instrumented mouth guards, for example. And what that's doing is then predicting the best metrics for measuring the actual strain of your brain, which that is the best metric, is the strain on the brain tissue. Now, obviously, we can't just measure that in real time. So she's doing some really good work on these models to try and predict that with certain metrics for things like rugby, football, MMA, boxing, Australian rules football. And she's showing that different metrics suit different sports first and foremost. So hopefully we can produce a good roadmap that if you're in this application, this metric suits this injury, so on. And that's where I think the future of the research is heading with it.
Based on that, though, do you think there are aspects of the research work that are consistent across the different standards? So we had a couple of questions about materials, for example, so trends for being lighter and lighter, in competitive environments, and do all design changes make the same change in each standard, if that makes sense, or are they so different that they have different results?
The standards are relatively similar within themselves. I think some people may have noticed when I was showing the BSEN 1077 slide, I had a bicycle helmet on there, and that's because it's the exact same impact criteria between the cycle helmet standard and the snow sports one. Actually, in field, those mechanics are very, very different. So we would expect to see very different changes in injury risk based on those design changes between the different sports.
Lovely. Okay. Thank you very much, Phil. Thanks for your considered answers there. Yeah,
Very
great
good,
job
Jeff.
on that one. Fabio, if I can bring you back in, we have a question about the influence of equipment on aerodynamics. I think we could talk about this more broadly, but specifically the question was about ski equipment, so the actual skis themselves, or the snowboard, the helmet and the boots. You spoke quite in depth about athlete position. So I wondered if you could maybe clarify the split, if you like, between the influence of position versus equipment, or if
Yeah,
there are any trade-offs there, and then potentially in other fields as well, what that looks like.
yeah, that really depends on the sport we are considering. And for example, what you didn't mention is also the suit. Like the suit is also influencing a lot because it changed by placing the roughness in different places, really changed the athlete. So in a ski, for example, the ski itself, it depends because it will generate friction. I go by heart. I think in a downhill, straight downhill section, 45% of the total resistance is due to aerodynamics. So the rest then is due for friction and others. So then when we talk about aerodynamics, of course, it's mainly the athlete body, which occupies a lot of the space, and also what is wearing, and then the helmet as well. Also, for example, is another type of sport. It's not winter sport. For example, in cycling, where I work most, what we see is that a bicycle, depending on the speed you are traveling, the impact is different, and it also depends on which type of bicycle you're riding. If you go to time trial, even the bicycle have like 15% of the of the total aerodynamic resistance, 15, 20. Other type of bicycle are more bulkier, so aerodynamic impact will be higher in percentage. So that is really depending on the sport itself and also the speed you travel.
Okay, but the interaction between equipment and athletes in terms of their position and let's say I think you mentioned about the downhill skier in the tuck position, the arm
Yeah.
forces were interacting with the leg there. So
Yeah,
there is an interaction that
yeah,
could be exploited potentially.
yeah. But just for example, now there were a lot of talks about, I think it was a UK helmet in luge. The luge, like the athlete is really inside. So there, I think aerodynamics 20-26%, which sounds small compared to the velocity, but because it's like a projectile, so that is why it's already very optimized. What the part that is outside, if it's like a closed luge, is like the helmet, or like if it's a single luge, okay, you have also the body part. And there also there are studies where to put the roughness patches on the skin. So it's really to optimize the aerodynamics on the body. And then,
So,
of course, the helmet, it's natural consequence that has also an impact.
and this is something really which is done. You mentioned the simulation there, but there's also the experimental aspects as well. And you mentioned the
Yep.
Silverstone Sports Engineering Hub. I wondered if you could just perhaps explain a little bit about that site, what they have there, the sort of equipment that goes about, or anything like that.
They have a wind tunnel specialized a lot on cycling, but yeah, from what I know, they also do some winter sport aerodynamics. I mean, from the short talk I had, and they had like a rig really specialized for luge and yeah, a skeleton and other sport like
Fantastic.
this. I don't work there, so I don't know really the
Yeah.
extent because okay, they don't. Yeah, they cannot disclose all the information, but I know that for sure they've done tests on skeleton luge in these other sports and
Okay.
cycling, of course.
We had a
Yes.
question on that one in the chat, so I just wanted to drop that in. And I should say for the audience, for those who might be interested in collaborating with some of our members or with the group, that each of our individual member universities have different facilities. We have
Yeah.
a similar wind tunnel setup at the University of Manchester, for example. So there are opportunities to engage with
Yeah.
us as a group on these kinds of activities too, if there are activities that you'd like to explore. Okay, I think we'll have to stop there with the questions, but I thank all the attendees for their wonderful questions. They're really interesting, shows really good engagement, and that you won't just sit there drinking a coffee while our people were talking. So that's wonderful. Fabio, you have a couple of slides just to talk about the Sports Engineering Seminar Day, which I alluded to at the beginning of the talk. So if there are further questions, ideas for discussion, we are holding an event next week. So we're a little bit late in advertising it. I think there's a wait list currently, but Fabio can tell you a bit more about it.
Yes. So next week we are going to have the Sports Engineering Seminar Day hosted at Watt University. The organizer are Professor Bloken, Dr. Dune, Dr. Hu, and myself, Fabio Malizia. And yeah, it's going to be hosted at Watt in the National Robotarium space. Now, we have also three keynote speakers. Dr. Tom Allen talking about metamaterials for sports application, Dr. John Hart about pioneering CFD in sports engineering, and Dr. Dario Cazzola from Invisible Monitoring to Lab on Video. So quite diverse keynote speeches. And the schedule is quite dense. We have two keynote speakers in the morning, then two breakout sessions with two breakout rooms talking about aerodynamics equipment. The first one is about mainly cycling, and then aerodynamics and performance. And then the second breakout room is more about biomechanics, movement analysis, and materials. And then last, we have the last keynote speaker from Dr. Cassola at the end. So we're already fully booked. So I don't know if there should be a waiting list. You can try to subscribe, but I don't know at the moment how many people already dropped. But I think not really many because it's quite an interesting. This is quite the list of all the talks that will be there. So it's really it looks really, not because I'm organizing it, but it really looks a very nice event. So when we were able to invite a lot of great speakers, and that's really really something that I'm very happy about it. And there is
Thank you.
also Will Dober and Tim as well. They're all
Yeah, thank you,
there.
Fabio. I was just going to back you up and say it's a wonderful event, but then both Will and I are scheduled to speak, so I think we're not unbiased, unfortunately. But yeah, it really is
Um,
genuinely as I mean, having started this in my engagement with this group was through one of these seminar days, and that's how everything began for me here. So I think that it's really a great opportunity, especially for students, to come and engage with the community. I should say that it's free to attend. You just need to get yourselves there. And yeah, once it's there, it's a wonderful place to meet people and network and start to learn a bit more about sports engineering within the UK. I think Will wanted to say something.
Yeah, if I could just put in as well, I mentioned our fantastic PhD student who's doing stuff on brain injury thresholds. Emily Chan is actually presenting in that second session, sixth presenter. So if people are interested in that, make sure to please attend that talk.
Absolutely. And just as a comment, if you aren't able to join this year because we're fully subscribed, next year, or 2027, I'll be hosting the next event at the University of Manchester. So we'll have an opportunity for people to engage there, hoping to bring some of our local partners in that area as well to the day to sort of give some insight into how, sports engineering is working locally and also within the community in Manchester. So lots of interesting stuff. It can have a real, I think it's clear certainly on the impact protection stuff, but in other ways as well. Sports can have a huge impact on the society, on people around you, and it's not just about elite competition. It's about grassroots sports, and it's about people first and foremost. So that's really what we're about too. So if you're interested in those things, please get in touch. If you can't join us at the seminar day, I think both of our speakers are very keen to connect with people. So please reach out to them on LinkedIn. They're both happy to do that, or by their email addresses. I'm sure you can find them online. And I'll just share a final slide, which hopefully you can see now, which is just a little thank you from me. So thank you for your time. I hope you found the session interesting and enjoyable. If you have any further questions, if we didn't quite get around to answering yours, please, you can forward it on to the contact details that are on screen here, or to us ourselves individually if you can find our contact details online, and we'd be happy to answer them. But yeah, I think that's basically it. So thank you very much for your time. Thanks for attending. And the recording of this session will be made available afterwards as well. So thank you very much and have a good day.